Okay, we're recording. Hello, my name is Sergio Garcia. This is my video for chapter 3 for part 1 of the test. I'm going to be quickly going over what I thought was important from chapter 3, which mainly had to deal with motion in 2 dimensions and 3 dimensions. So I'm going to do like a general basis of what you need to know. So this chapter is extremely similar to the chapter that came before it, chapter 1. Except actually, I'm sorry, chapter 2, but it actually implements some things of chapter 1. And I'll explain what I mean. So right in front of you in these 2 boxes, oh, whoops, that's not my vanishing pen. In this box right here, in this box right here, we have equations that you saw in my last video. The reason why is because they're still very much applicable today. These equations right here are basic kinematic equations. They will help you navigate your position, your velocities, your acceleration, your time. You'll be able to calculate any one of those variables using these depending on what's already been given to you. I already went into depth onto how to manage them on my last video. So I'm not going to go too much into it now, but I will be sort of roughly going in what situations they are helpful. And they will be helpful. Next, we have our free fall equations. This looks pretty familiar. Essentially, when I say free fall equations, it just means any equation where an object is being moved, thrown, dropped in our Earth's gravity. So anytime, let's say like a ball is thrown, a ball is dropped, of anything really, an egg is tossed, a pillow is thrown across the room. That's where this comes into play. And the way you can tell is you look at the acceleration of this and you see it's negative 9.8 meters per second squared. That is our gravity. Again, it's important to note that when you look at your acceleration on Earth, you can separate that into 2 components. When you look at acceleration down at the negative 9.8 meters per second squared, you have to again remember that it's going down, no other direction. We treat our Earth in physics like it's a flat plane rather than a circle. I'm sorry, a sphere. So when you break it up into pieces, it's 0 in the I or X direction and negative 9.8 in the J or Y direction. Really, this is me just going over what I've said before in the last video. So when it comes to your X side, I already separated them. This is your X, this is your Y. When you integrate this 0I, for your velocity of X, it is just your initial velocity of X. And then when you're looking for the position of X, it is the initial velocity of X times time plus your initial position of X. And for the Y, there's a bit more to go about it because remember, we have to contend with the acceleration going down in the Y direction. So our velocity in respects to our velocity of Y in respects to time is negative 9.8 t, because negative 9.8 is our acceleration, times the time, plus our initial velocity, and then our y of t, or our position of y in respects to time, is negative 9.8 over 2, which is close to negative 5, times t squared, plus your initial velocity times time, plus your initial position of y. So again, this is just a review of what we discussed in the last chapter. Now, where does this come into play? So as you know, in the last chapter, we discussed movement essentially in a straight line, but what happens when gravity comes into play in terms of this? So, or like what happens when our velocity has more than one component? And we'll talk about it, right? So that's the major distinction in projectile motion, is that our velocity, not just our acceleration, will be treated with 2 different components to it. And I'll show you with this really basic rudimentary example right here. If I can switch pens really quickly. All right, so we're about to get started. Okay, so it's important to, okay, so we're gonna look right here. I'm gonna see our graph. This is velocity, this is time. So we see right here that we have, let's say it's a football, right? A football is kicked with the velocity initial of 98 meters per second, right? Meters per second at a 30-degree angle. with this, we can see a couple things. We can see that as the ball is kicked, it's arcing and then eventually falling down, right? That means that it's, it's being kicked at our own Earth's gravity. So we know that because the ball is falling, it's affected by gravity. So it has an acceleration of negative 9.8 meters per second squared. And that is standard, right? We know that's just how it works. In situations and problems like these, I found it to be most helpful to look for time first before you do anything else, because that's just really useful for any one of these equations. You can see that 1, 2, 3 of these equations each have time. So it's good to find time first with what you're given and then work from there. So how do you go about finding time, right? That's your first question. Well, if you can see right here, we have a velocity that's moving in this type of vector, but we don't really know which way it's going, or like how high it's going and how far to the right it'll be going in terms of velocity, like how fast in the y direction and how fast in the x. And that's where we separate it into components. We're given the angle of 30 and the velocity or speed of 98, and we can work with that. So we can do our v of x. I'm sorry, we'll split it up like this. So our vector v is equal to 98. And then we see right here, let me get my vanishing pen, that we have a line right here, right? That is our y component. And this right here is our x component for 98, the vector 98 meters per second. So we can like calculate that better. We split it into components. So if we wanted to get this line right here, that is our vx vector. We would use 98 cosine 30 I. And then we add that to our vector vy, which would be 98 sine of 30 j. Now, if we calculate that, we know that our vector v, this right here, is actually 84.9 meters per second in the I direction, plus it's 49.0 meters per second in the j direction. And that's how we split it up. Now, you're wondering, what do we work with that? So if you look up here, we know that we have formulas. If I get my vanishing pen, formulas that can work with our v of y and v of x. We can now use those to properly function. So I'm going to use this space over here in a different pen. Right? So let's say you wanted to find the point right here. Oh, well, let me establish a basic, right? So when you look at a graph like this, or a situation where something is being thrown, it's good to find out what the boundary of the object is. For this football, the only time the football stops its trajectory is when it hits the ground. When it hits the ground, its position y is at 0. And the easiest way to find that first is to find the time at the apex of its launch, right? So if we were to draw a line right here, we can first find when the velocity of y is equal to 0. So how do we do that? You may be asking. So we take our equation v y, this one right here. I'm sorry, wait, no, not that one. We take this equation. Yes, so we take Vy is equal to our Vy initial plus our acceleration times time. And then we set our V of y to 0. So we're finding when our velocity of y is equal to 0, as you can see, to get our answer. So we know that our y component is 49 meters per second plus our acceleration, which is negative 9.8. And then we're looking for our time where this is equal to 0. So how do we find that? Well, we do a manipulation, and it'll equal to t equals to 49 over 9.8, which is equal to 5. So if it's at this height at 5 seconds, we know that the full duration of this, if this is the halfway point, this is 5 seconds, this will be 10 seconds. Its full launch duration will be 10 seconds. Now, let's say you wanted to find the height at this point, whatever that might be. We can do that as well using what we just got in terms of time. Remember, time is typically the most important thing to get for one of these equations first, so that you can work with all of your other equations next. So if you want to get that right there, we would use the equation change. And in this case, it says x, but it's a change in y because we're working with this, right? So if we wanted to find this point right here where it's tallest, we would do our change in y is equal to our average velocity times the time that we just found. So y is going to equal to average velocity in this situation would be our y velocity divided by 2. So that would equal to 24.5 meters per second. I'm not going to write the units because it's too much, times our 5 seconds. And that means our change in y is going to equal to 122.5 meters. So this right here is a height of 122.5 meters off the ground at 5 seconds. So the apex of the football is reaching that height after 5 seconds. And after 10 seconds, its height will be 0. Another thing you could ask is, at what angle is the velocity going when it reaches the ground? And that's a good question. I'm going to quickly erase a couple things. Again, if you need to go back, you can always just back up in the video to see how I got these answers. I'm going to erase this right here because I wrote it right there as well, so it's okay. We'll get a different pen. Now, the best way to look at this is to see its angle going which ways at this point. So we know that our x portion of the velocity is 48.9. And you know, from these situations, there's nothing affecting it. Since there's no like wall right here that's blocking off our x from moving, and this is a vacuum, there's no air resistance, just gravity. There is no reason for which 48.9 would change. So we know that its x component for the velocity's angle will be 84.9 still. However, we see this is the opposite side of the graph for a velocity of 98 meters per second. And we know that it's essentially a mirrored image. So if it's in this situation, the v of y component is 49 meters per second. In this situation, it would be 49 meters per second in the negative direction. So it's a negative 49. And then from there, we could sort of add the vectors together. So let me back up, because I can draw this arrow instead of being right there. I can draw it right there. 49 in the down direction. Now with that, we can calculate sort of an angle. And if you were to toss that into your calculator, tan inverse of 4984.9, you would essentially get theta equaling to, it would essentially be 30 again, but under the x-axis. So essentially, its true, I guess, angle would be 330 degrees if we were looking at this graphically. So this right here is 30. It's a 30-degree angle, but it's going down instead of up, right? So 360 minus 30 is 330. And those are essentially the majority of things you can do in these types of problems. There are slightly more advanced things, but these are the general bases. Everything else sort of comes and follows off this. So that's all I had to say on the matter. I hope this was informative and that it'll help me learn. Alrighty, thank you for your time. Thank you for watching, and goodbye.